Hello, everybody. Welcome to the Minisymposium on set propagation methods in Julia, techniques and applications at JuliaCon 2021. It's my great pleasure to be the moderator of this panel, this workshop, this Minisymposium, which has been organized by Marcelo Forets of the Universidad de la República in Uruguay and Christian Schilling from the University of Constance in Germany. They've done a really great job of putting together this set of speakers from across the Julia community who are all working in different aspects of set propagation. And we're very excited to have Goran Frehse as the first speaker of the session. So he was an associate professor at the Université Grenoble-Alpes in France, and he is now at the Hybrid Systems Semantics Group at ENSTA in Paris. He is the architect and lead developer of two popular model checking tools for hybrid and cyberphysical systems, which are PHA-Ver and SpaceX. And so all of the talks, there are 6 talks in total, each of between 10 and 15, 20 minutes length. They're all pre-recorded talks, which I will be playing. And then after each talk, there will be a short question and answer session. And so please feel free to ask questions on the set propagation channel on the JuliaCon Discord server. You'll need to register for JuliaCon to get access to that. Okay, so I'm going to play Goran Frehse's talk, which will be an introduction to the subject. I should also mention that Marcelo and Christian gave an excellent workshop the other day at JuliaCon, which is on YouTube, on an introduction to set propagation methods using their Julia Reach packages from the Julia Reach organization for reachability analysis with Julia. Okay, let's get started. Just 1 second while I load the video. Oh, and here is Goran Frehse. Would you like to be hi? Please.
Hi.
Would you like to be visible during your talk?
No, that's fine.
Okay. Okay, then I'll put you back on once the talk is finished. So for the question session, thanks. So just 1 moment. Here we go.
Hi, I'm Goran Frehse from Paris. In this talk, I'll give an introduction on how set propagation works to verify safe behavior in cyberphysical systems. First, I'll give the context, which is model-based design, and how formal verification fits in this process. Then I'll compare simulation with set propagation. I'll introduce the hybrid system paradigm and list the set propagation operators that are necessary. Finally, I'll conclude. This is the model-based design process in industry illustrated on the V model. Starting from higher level requirements, I'll introduce the hybrid system paradigm and list the set propagation operators that are necessary. Finally, I'll conclude. This is the model-based design process in industry illustrated on the V model. Starting from higher level requirements, one builds high-level models, details those models to a lower level, and finally to the implementation. Afterwards, there's tests that check whether the system satisfies the specifications which correspond to the models on different levels. Now, the goal in industry is to place these tests at the end of the development cycle with checks that are carried out on the model level, so as early as possible and on a high level as high as possible. This is called front loading. And this is where simulation and verification on high level models like the ones that we discussed today comes in. The question that formal verification tries to address in model-based design is how to guarantee the absence of bugs, instead of just finding some bugs, but maybe not all of them. The difficulty is, in our case, that we have a continuous dynamic system that is subject to bounded uncertainty, for example, in the parameters or noise, and that there are discrete events. We talk about this later on. We use methods that are inspired from formal computer science, such as abstract interpretation, model checking, and compositional analysis. A little example. Take this helicopter that is controlled to reject wind disturbances. We have a 28-dimensional model of this helicopter that includes the flight dynamics and that is stiff and highly coupled. So assume you've built a controller. How do you check that it works? The standard industrial practice is to simulate the system, meaning that you pick an initial state of the system and you compute a trajectory that corresponds. Here in this image, we show the vertical velocity of the helicopter and you want to check whether it remains below this red bar over time. Now, this is the case for the shown trajectory. The question is, what happens if you start from a different initial state? So let's say we pick 1,000 different ones, each one gives a different trajectory. And so we see that some of the trajectories actually approach the red line, but we still don't know whether there is not one of these that actually exceeds it. With set propagation, we don't compute just a single behavior. We can start from a whole range of initial states. A dense set, so technically it contains an infinity of trajectories. And we compute a cover, meaning a sequence of sets, that enclose all of these trajectories over time. Here in this image, it's the blue envelope that is shown, and if we zoom in, we see that it actually stays below the red line. So the system satisfies the specification. So in simulation, we deal with deterministic behavior in the sense that we can only compute one trajectory for one set of circumstances. If you want to cover more circumstances, then you need to generate more trajectories. In set propagation, everything can be non-deterministic because anyway you're covering things with sets. So you could have continuous disturbances, implementation tolerances, and so on and so on. Now, the advantage of a simulation is that it's scalable even for complex nonlinear dynamics, while set propagation is scalable basically for linear dynamics and is very difficult for nonlinear dynamics. Let's illustrate how difficult it is to cover all cases using simulation. So in corner case simulation, one checks all the extreme points. Let's say we have n variables, t time steps, which gives us, for an initial set that is specified with intervals, we get 2 to the n vertices. And for the inputs, also specified by intervals, we get 2 to the m vertices. Now, over t time steps, this gives us 2 to the n times 2 to the m to the power of t trajectories. So it's exponential in time, and that is really a killer. On the other hand, techniques from template reachability, so basically computing interval enclosures, have been shown that they can be computed linearly with time. So we have just one operation to do with each time step, and that operation is cubic in the dimension. Now I'll talk about applying set propagation to cyberphysical systems. Mathematically, we talk about hybrid systems, which mix discrete events with continuous evolutions, for example ODEs. This modeling paradigm captures complex behaviors that are encoded with just a few simple operations. The hybrid systems paradigm is amenable to fortification using set propagation. A few examples from projects that we worked on is assisted automatic driving, human-robot interaction, smart buildings, chemical batch plants, analog mixed signal circuits, and autonomous drones. The semantics of a hybrid systems are characterized by its continuous discrete behavior. The system evolves with time according to dynamics specified by ordinary differential equations. This dynamics can switch instantaneously and the state can jump instantaneously. So we get an alternation of trajectories here shown in blue, and then the state can jump to some new state, and then time continues to elapse. The simplest model of a hybrid system is the bouncing ball. So we have a ball with a certain mass, and it's held at a certain height, and when you let go, the ball falls to the ground, and the ground repels the ball bounces back up, and so on. The hybrid automaton model is a simple way to describe this sort of systems, and here we have basically an automaton discrete state in which we inscribe the differential equations that characterize the system. And then we have state transitions, here this arc that's associated with conditions. So when does this transition happen? Here it happens when the ball is on the ground and the speed is negative, so it's falling towards the ground. And the effect of the transition is that the speed reverses, so the ball bounces back up. The discrete state is often called a location. Then there's conditions that describe when one is allowed to stay in this location. So here the invariant is that we are always above ground, and the ordinary differential equation is called the flow. So here is a illustration of what happens with the ball when you let it go. It falls to the ground, it bounces back up, and so on. And you see the alternation of continuous trajectories and then instantaneous jumps. In the velocity plot on the bottom, you see that there is a discontinuity. When the ball hits the ground, the velocity changes sign, and so you get a discontinuity there. Now we look at these trajectories not over time, but in the state space, meaning we have the position x on the vertical axis and the velocity. On the horizontal axis, it's the exact same trajectory, so it falls to the ground, then bounces back up, and the sign change here introduces a discontinuity. Now this state space view has one advantage, and that is we can draw it over infinite time, right? So we can plot all the pixels that we get if the ball bounces infinitely often. Now in set propagation or reachability, we do the exact same thing, but for a whole set of initial states instead of just one state. So we get these bundles of trajectory. This is also called the flow pipe. And then we have to identify the states that can jump, okay, to compute the image with respect to that jump, and then propagate again by solving the ordinary differential equations to get bundles of trajectories. So here's a case study that's a little bit more complicated than the bouncing ball. It's an electromechanical brake that we looked at together with Bosch. So there's an electric motor that moves the brake caliper towards the brake disc, and you want to be sure that the braking force is large enough when the brake is activated within a given time frame. And now the thing is that the control of this electric motor is supposed to take place on a multi-core processor, so there's scheduling involved, and there are certain guarantees on the scheduler that vary with time. And the question is, do you always execute the control code enough to allow this brake to close? And there's a simple automaton model that captures the scheduling here, so in terms of the times where the control code is executed. And we put this together with a physical model of the plant and the control code. This is different from classic analysis, which would separate the two concerns completely. So there would normally be a timing analysis of the software and then a closed loop verification of the controller. Instead, we put the three together. So we have a scheduler model for the execution of the code, then the control code as a model, and then the physical plant model. And we put all of this together. So here is a set of behaviors. So starting from the initial position, the brake caliper is supposed to close within the 14 milliseconds. meaning it's supposed to reach this red line here up top. And now because of the scheduler, the controlled code is not always executed at each cycle. So it could be activated here in the beginning immediately, and then so the break starts closing, but it could also miss a cycle and start in the second cycle, or one more and start in the third cycle. And because of the guarantees of the scheduler, we know that if you've missed 3 events here, then we don't miss another one. Okay, so there's several. It's basically a tree of behaviors of which events could we miss in terms of executing the control code. Here is a slightly modified system. We artificially introduced a fault by tweaking one of the coefficients. And what's interesting about this is that out of this tree of behaviors that we get, there is only one branch that fails, and it fails catastrophically, meaning that the break actually never closes. It gets close to the closing target, but then it goes back away from it. So what are the basic ingredients needed for set propagation? We start from an initial set R0 and then carry out a fixed point computation where at each step you compute the post operator, meaning the successor states for our current set, and then add this to the current set to get this reachable states for the next step. And the goal is to have this eventually converge to a fixed point. There are 2 types of post operators in our hybrid system. One is the time elapse, which we can compute either with fixed or variable time step. And the other is the image of the discrete transitions. So in the fixed point computation, we accumulate new states that we add to the reachable states. And we want to check whether at some point we terminate. So we need a containment check and an emptiness check. So you can look at this as a tree. So starting from the root node, which is our initial set, we compute the successor states, and this would span an infinite tree. Now, if in one of the nodes we can show that the set that it represents is actually a subset of one of the other states, we don't need to follow that tree, and so this prunes it and turns it into a finite tree. Okay, so sometimes the successor state can be empty. For example, if one of the jump conditions in a discrete transition is not satisfied, and sometimes they can be contained in previously visited state. So ideally, we end up with a finite tree in the end. Finally, oftentimes we wish to intersect with bad states to see if undesired behavior is present in the system. So set propagation is a technique to compute an exhaustive envelope of the behaviors of the system, something we call also the reachable states of the system. The set propagation replaces a very, very large number of simulation tests to achieve coverage. It can account for uncertainty in a wide variety of ways, including modeling errors, operating conditions, and environment and user behavior that can be non-deterministic. The set operations that are required are computing the image with respect to time elapse, so solving the ODEs, and with respect to the discrete events. The discrete events are often just linear maps, so they can be relatively easy. We also need containment and emptiness checking for termination and reducing the complexity, basically reducing the number of sets that we have to compute. The challenge in practice is to balance the accuracy of these computations versus the compute involved. Thank you for your attention.
Well, great. Thanks very much to Professor Frehse for an excellent talk, excellent introduction. So far as I can see, I don't see any questions on the Discord server, please do feel free to add questions there. That's the set propagation channel on the JuliaCon Discord server. So I do have a question. I come from interval arithmetic, and so I was wondering to what extent you can, of course, it's the eternal question in this subject, how can you reduce the overestimation of these sets that you're propagating, which usually will just expand over time?
So basically, we looked a lot at piecewise linear systems for exactly this reason. So it turns out that for piecewise linear systems with some algorithmic tricks, you can pretty much get around this. For nonlinear systems, I've banged my head against the wall for a long time, and finally. Finally, the only systematic solution I found was to split the sets of states into small enough states that you get convergence, and that's the standard thing that you do, and it seems that's what you have to do.
Right. Okay. And then you end up using sort of higher precision arithmetic as well, or?
We did this in some of the works. We used high precision, so arbitrary precision integer arithmetic, and then of course you ended up with just memory problems because you get these huge numbers, and so we looked at some over approximation techniques to reduce this. So to approximate the large number formulas with small number formulas. So that was one of the tricks. The other one would be the scalable one, I think, is using integral arithmetic and then just rounding in the right sense.
Okay, great, thank you. Do any of the other panelists have questions? I don't see any other questions on either YouTube or the Discord channel. Oh, yes, there's a question. How high can you go? This is from Amanda Gray, is one of the panelists. How high can you go in dimension?
That's a little bit of a tricky question because it really depends on the dynamics of the system. Okay, so the advertisement statement is that we went from a handful of variables to hundreds and then to 10,000s, and for a simplified version of the problem, people have pushed this now to a billion, I think. But of course, there's the downs, or the other phase of it is that you can make a three-dimensional chaotic system that is completely impossible to verify. Okay. Where are typical practically relevant application? That's, for me, that's actually an open question. There has not been that much really practical work on real examples that I have an authoritative statement there. There's some practical problems turned out to be surprisingly easy, and others are just completely impossible.
Right. Yeah. Okay, great. Thanks very much. So I think we need to move on to the next talk. We may be able to have another question and answer session right at the end of the Minisymposium after all the talks. So thanks very much to Goran Frehse again. So now we're going to move on to the second talk, Dionysus.jl, Optimal Control of Cyber-Physical Systems, by Benoît Legat, Guillaume Berger, Julian Calam, and Raphael Junges. And I believe that the speaker will be Julian Calam, who's a PhD student at the Institute of Information and Communication Technologies, Electronics and Applied Mathematics, IC team of the Université Catholique de Louvain in Louvain-la-Neuve in Belgium. Okay, so hi, Julian.
Hi, thanks.
So I'm going to play your video, and then we'll have a question session again. Thanks.
Thank you. So hello everyone. So in this talk, I will present the Organisers software, which is produced by the ARC project Learning to Control. So the objective of this platform is to control complex dynamical systems, such as a drone, which evolve in a complex environment and subject to external disturbances. So we want to derive a generic procedure to design efficient controller to achieve complex specification. So to achieve this objective, we will rely on several powerful tools, such as the formal method, the learning-based methods, and the optimization-based methods. But today, I will focus only on formal methods and more precisely on the abstraction-based method. So for this presentation, we will consider the following framework. So we consider a nonlinear dynamical system depending of the state X and the control input U. And there is also external noise which can be bounded. Then we will focus on the following specifications. So first, the invariance or safety problem. So given a subset of the state space, we want to control the system in such a way that it will remain in that set for a given period. And the second specification that we will consider is the reachability problem. So for which, given an initial set and a target set, we want to drive the system from any state starting in the initial set to a state in the target set while avoiding the obstacles. So as I said before, to design such a controller, we will rely on abstraction-based techniques. So the idea behind these techniques is to discretize the different variables to transform the model into a simple combinatorial problem on a finite state automaton. So there are basically 3 steps. So given our original system, which is typically a continuous system, we will first build an abstraction of it, which will be a kind of automaton, but in a way that there is a particular relation between the two representations. I will explain just after what is the meaning of this relation. We will also build new specification for the abstraction, and then we will solve the control problem for the abstraction and this new specification. So this is easier because it is a simple combinatorial problem. And finally, because of the special relation between the two systems, we can derive from the symbolic controller a controller that will work for the original system under our original specifications. So we will now consider discrete time control system. So it is simply described by a triple. So the set of states, the set of input, and a transition relation. So it means that being in state X and applying the input U, the system will potentially reach the state X prime. So I said potentially because as the system is non-deterministic, we could reach more than one state. And so we'll denote by these notations the set of destinations that we could reach being in state X and applying the input U. And we call this set the post-image of state X under the input U. And so, as I said before, there is a particular relation between the original system and the abstraction, so which is called an alternating simulation relation. So we will not enter too much into the detail, but simply the idea is the following. So given a system S1 and a system S2, we say that a state of S1 is in relation with the state of the system S2 if for every input U1 of S1, there exists an input U2 of S2, such that every state in the post-image of X2 under U2 is in relation with at least one of the states of the post-image of the state X1 under the input U1. And so basically it means that for any trajectory of the system S2, there exists a related trajectory for the system S1. So if such a relation exists, we say that S2 is an alternating simulation of the system S1. So now we can go into the details to see how we built in practice the abstraction. So we have our original continuous state space, and then we will discretize it into small cells. And we will associate to each cell a symbol which will be the discrete state of the abstraction. And then for a given input, we will compute the reachable set of the cell, but in practice, it is really difficult to compute precisely, and so we will compute another approximation of the reachable set, typically an hyperrectangle. And then we will add an hyper edge in the abstraction for all the cells which have a non-empty intersection with this other approximation of the reachable set. And the hypergraph resulting from this procedure for every cell and every input is the abstraction. So we use what it is called the quantization relation. So given a state in a continuous state space, it will be related to the symbol associated to the cell in which it is located. And we can prove that this quantization relation is in fact an alternating simulation. So the original system is an alternating simulation of this particular abstraction. And because in the point of view of the abstraction, we don't know precisely where we are, we just know that we are somewhere in the cell. And so by applying the input u, we can potentially reach any of these discrete states. That's why we have an hypergraph. And so we have some additional non-determinism resulting from the discretization of the domain. And as you can imagine, the size of the cell is really important. So for example, considering this coarse level of discretization, we have in black the obstacles. And in the point of view of the abstraction, we will consider as obstacle all the cells that have a non-empty intersection with the obstacle. And so with this level, we see that it's impossible to go from the left to the right. But if you use a finer level, we see that it seems possible to go from left to right. But because our over approximation here of the reachable set of the cell is not precise enough, we could have an hyper edge which has some destination as obstacle. And so it is too risky to take this hyper edge into point of view of the abstraction. And so we cannot be sure to control the system from the left to the right while avoiding the obstacle. So again, it's a failure. And by reducing again the discretization step, we can finally guarantee to go from the left to right. But the problem is that the number of cells grow exponentially with the dimension of the state space. And so we suffer of the curse of dimensionality. So there is really a trade-off between the size of the cell and the accuracy of the over-approximation of the reachable set and the execution time. So for example, we could use high accuracy methods such as set propagation techniques that we can find, for example, in the reachability analysis.gl package, where the idea is to iteratively propagate a sequence of sets starting from the set of initial states according to the system dynamics. But in our case, it is too slow. That's why we choose less precise but faster method based on property of the system, such as the incremental stability. So basically, we can use the fact that trajectory starting with quite close initial position will at the end remain close. But more generally, we will try to compute what we call a Groband function. So we have our cell and the center of the cell is C. And what we will do is we will compute the trajectory of the center C of the cell, in the case where there is no noise. And the Groband function, which is the beta function here, is a function which will give us an upper bound on the distance between the image of any state starting in the same cell and the image of the center of the cell. And as you can see, this function is parameterized by a set K, which is in fact the region of validity of this function. And so the advantage of using this over-approximation technique is that it can be locally dependent thanks to the set K, and it allows also to depend of the input U. And so it remains the problem of computing such a Groband function. So to do that, we have a useful theorem. Simply, it states that by bounding the Jacobian of the vector fields of the dynamics in a region which contains the trajectory, which can derive such a Groband function. So in the particular case where we can find precise bounds on the Jacobian which are independent of the state, it is very efficient. So indeed, we just have to evaluate this bound for every input only once at the beginning. And then the Groband function will be the same everywhere in the state space. And so this is, for example, the case for this dynamical system. But in the case where it is not easy to find a common precise upper bound on the Jacobian, we will have to compute a local bound depending of the position in the state space. And to do that, we will use interval arithmetic. So we want to compute a valid Groband function for the subset K of the state space. And to do this, we need two bounds we need bounds on the Jacobian that are valid for all the trajectories starting in the set K. And so we will try to identify the smallest set K prime that contains all the trajectories starting in K. And then we will compute a bound on the Jacobian in that set. So we start with the set K prime equal to the full state space. And then using the interval arithmetic.gl package, we will evaluate the highest value of the vector field on that set. And then we'll compute a better approximation of the set K prime. And we can iterate several times. And at the end, we end up with a fairly accurate region K prime, which contains the trajectory starting in K, and then which we will evaluate an upper bound on the Jacobian. And then we can compute the Goran function, which is valid, so for every cell which is contained in the set K. Note that we have the abstraction. It remains to derive the new specification for the abstractions. So simply, we consider as obstacle all the cells which have a non-empty intersection with the obstacle of the original problem. And for the initial set, we consider all the cells which contain the initial set. And for the target cell, we consider all the cells which are strictly contained in the original target set. It just remains to compute the symbolic controller, which is easy because we just have to solve a fixed point equation. So for example, for the reachability problem, we start with the target set, which is in blue here. And then we will add a cell in the current target set if for one input, all the destinations are fully contained in the target set. So for example, for the cell C1, we have the control input U2 that guarantees to reach the target set. So we can add C1 in the current target set. But for example, for the cell C2, it is not yet the case because there is no input for which it is fully mapped inside the current target set. And so we expand the target set, so the region which we have for which we have a control sequence to the original target set progressively until covering the initial set. But as said before, computing the whole abstraction is suffering of the curse of dimensionality. And so our idea is to compute lazily a small part of the abstraction by co-designing the abstraction and the controller at the same time. So we have still our original system, then the abstraction which is an hypergraph as presented before. But now we will build another abstraction which is simpler. So instead of adding an hyper edge, we simply add several simple edges. So this abstraction is an hypergraph, while this one is a simple graph. So this one can be seen as an adversarial problem. So we choose the input, but cannot choose the destination. While this one can be seen as a collaborative problem. We can choose the input and the destination. We will also define a cost function of x and u, c, which gives the cost of applying the input u in state x. So our goal is now to still achieve the specification while now minimizing this cost function. And with our previous abstraction, we can compute an upper bound on the cost of achieving the specification starting from a particular cell, while this new abstraction, which can be proved to be in fact an alternating simulation of the original system, will provide us a lower bound on the cost. And in fact, we will use it in order to get a heuristic to guide the construction of the second abstraction. So the idea is to use an I-star algorithm working on hypergraph. So we will build the abstraction lazily, starting from the target set and guide to the initial set thanks to the heuristic obtained via the simple abstraction. So we will use a priority queue n, which is initialized with the cell of the target set, with a cost given by the heuristic, and for the other cell, for which for the other cell, the cost will be set to infinity. And we have also a set C containing the cell for which we have a control sequence, and a set O for which it contains the cell for which we have the optimal control sequence. And we pop the first element of the priority queue. So imagine that this is this cell in blue. And then for every input, we compute the preimage of this cell. So it means that this is the preimage of this cell. So it is all the cell for which the post image of this cell has a non-empty intersection with our current cell Q. And so for all of this cell, here, we compute the post image if it's not already done. And if the post image is fully contained in the control set, then we can add this cell into the priority queue and update its cost. And we iterate in that way until all the initial cells are inside the optimal control set. And so at the end, if the heuristic is consistent, we end with the best worst case hyperpath. So here you have an example of the execution of the algorithm for a simple two-dimensional dynamical system. So first we compute the simple abstraction on the whole state space, and from it, using the Dijkstra algorithm, we can deduce a heuristic cost from which gives the cost from any cell to the initial set. And then we apply the A-star algorithm to compute lazily the abstraction from the target set to the initial set using the heuristic. And in dark blue, you can see the cell for which we have the optimal control sequence. In light blue, those for which we have a control sequence. And in yellow, the cell for which we compute at least one transition. And so, as you can see, we compute only the abstraction on a small part of the state space. We can use also this algorithm in a greedy way, so giving more importance to the heuristic. And in that case, it's no longer a consistent heuristic, and so we lose the optimality properties of A-star. But we can potentially reduce drastically the number of transitions computed. So we can see the result here on a three-dimensional system. So we can go even further in this idea of reducing the part of the computed abstraction by using a three-level partition of the state space. So the cursor level will be a simple graph abstraction. Then in each big cell, we will potentially build a medium level abstraction, which again will be a simple graph abstraction. And the final level will be the hypergraph abstraction. And so the idea is to use a branch and bound at the cursor level in order to reduce the number of big cells in which we will build the finer levels. So when we fixed a path at the cursor level, we can compute several controllers, one from the first cell to the second cell of the path, then another to the second cell to the third, etc. And it has the following advantages. So as we have local target into the state space, A-star will explore less nodes. Also, each controller can be computed in parallel using different threads. If two paths at the cursor level have a common path, so it is the case here, then we can reuse the path controller, so for example the two first. And we have also more flexibility as we can change the size of the discretization between two big cells, reducing the size in complex region and increasing the size in simple region of the state space. And so as you can see here, the execution of the algorithm on the simple two-dimensional system. So as you can see, we compute the abstraction on a smaller part of the state space. And finally, you have here in the table the total number of transitions computed by the three approaches. So the one computing the full abstraction, then the one using the A-star algorithm, for which we have some additional transition for the heuristic, and then the one of the hierarchical abstraction, for which we have the additional cursor level. And as expected, the number of transitions has decreased. So thank you for your attention and feel free to ask questions.
Great. Thank you very much, Julian, for a very nice talk. Let me add you. Hold on. Sorry, I'm struggling with the technology here. Okay. So are there any questions for Julian? So am I right that you are using a combination of sort of forward simulation and backward simulation, let's say?
Yes. Yes, we need to compute the post image of a cell and also to be able to have an idea of which cell can reach some part of the space.
So do you use constraint propagation techniques for that, for the reverse part?
No, for the reverse part, we use the same techniques than for the forward part. we just use the opposite dynamics of the system to.
But that supposes that the dynamics is invertible?
Not necessarily, I think.
What do you mean by the opposite dynamics?
Instead, to compute the pre-image, instead of using the dynamical function f, we use the dynamical function minus f.
Minus? What do you mean by minus f?
So we just change the sign of each components of the mapping function of the dynamical system.
Right. Okay.
Yes.
Okay, there's another question from Christian. How does this compare to other approaches to the problem?
Sorry?
How does your approach compare to other different approaches to the same problem?
So for the moment, we focus only on still a small dimensional system. So for 3 or 4 dimensional dynamical system. And so here in this work that I present, we only compare with techniques based on the abstraction techniques. And so just comparing the number of transitions computed in the abstraction. Yes.
Okay, great. Any other questions from the other panel members? I don't see any other questions from the audience. If not, I think let's move on to the next talk. So thanks again to Julian. Thank you. Okay. So, sorry, the next talk is by Ander Gray. Let me add Ander to the stream. Hi, Ander. So Ander is a PhD student at the University of Liverpool in the UK. And I'm going to play your video. So the subject is computing with sets of probabilities in Julia.
So in this talk, I will present the Organisers software, which is produced by the ARC project, Learning to Control.
I'm Ander Gray from the University of Liverpool, and big thanks to the guys at Julia Reach and Julia Intervals for organizing this mini-symposium on set propagation in Julia. This presentation is about computing with sets of probabilities in Julia. I'm going to be talking about one package in particular, probability balance analysis, or PBA for short. And what it essentially is a Julia implementation of p-box arithmetic. And what this package does is, in a sense, it combines probability theory with interval arithmetic. And what it gives you is an intrusive arithmetic with distributions and sets of distributions in the same sort of fashion that interval arithmetic does with sets. So before looking at sets of distributions, I think it's useful just to tell you what the story is like in probability theory. So you can have some random variable which is described by its PDF, its probability density function. I think people are most familiar with the PDF, but an equally valid representation of this random variable is the CDF, or the cumulative distribution function. What this function gives you is the probability that the random variable is less than or equal to some value of x. So in this package, all of the random variables are described in terms of their CDF. There's a couple of reasons for this. The CDF is useful mathematically for a couple of reasons. For example, if you want to take a sample of this random variable, what you can do is you can take a uniform random number and then slice this CDF, or evaluate its inverse at some random value, and what you get is a sample of this random variable. Also, if you want to compute the probability that this variable is in some set, for the density, what you'd have to do is you'd have to integrate this function in this set using quadrature or Monte Carlo or whatever. For the CDF, it's much simpler. What you do is you just evaluate this function at the endpoints of the interval, and you just subtract the values. So for example, for this set here, the probability measure, the probability that the random variable is in this set is about 0.61. All right, so this is what the story is like for precise distributions in probability theory. When I say a set of distributions, what I essentially mean is that an interval or a set value is going to be returned for this probability measure for some set. So there's a whole bunch of different models that you can use for representing a set of distributions. The simplest and in some ways the most crudest are intervals. So if you take the CDF of an interval, what you get is this sort of this box in the CDF domain, and the way it bounds a set of distributions is, okay, any distribution function whose CDF falls in this box is going to be a member of the set, member of the interval. For example, what's shown here is an example of a distribution which is in this set. Here's another one. Here's another one. The interval, of course, also bounds precise numbers, scalars. But essentially, any arbitrarily shaped distribution function which falls in this box is a member of the set. And okay, now when you ask for the probability measure in some region of this space, for example, at the edge region of this interval, you get not a precise value for the probability, but you get this interval. In this case here, it's just the interval 0, 1. You also get 0, 1 if you ask internally in the interval. Of course, when you ask over in some region outside of the interval, you're going to get probability 0. Or if your set encloses the interval completely, then you're going to get probability 1. So that's a kind of a crude model of a set of distributions. You get zeros and ones, or the interval 0, 1. But if you're happy enough with that concept, instead of making the bounds of this box step functions, but if you make them distributional, so you make the bounds of this domain distributions themselves, you get a much more flexible model. And this is what you call a probability box or a p-box. And it bounds a set of distributions in the same way as an interval. Any distribution function whose CDF falls within these bounds is included in the set. So in Julia, you can use probability bounds analysis, and you can make these p-boxes by calling a parametric constructor, in this case a normal distribution, and giving it interval parameters. So the one that's shown here is a normal distribution whose mean is an interval and a precise variance. And okay, it's got this kind of two interpretations. So if I now take a horizontal cut of this p-box, instead of getting a precise number, I get an interval, and I can do that by calling this function cut. I can also take a random sample of this p-box. A random sample of a p-box is now going to be an interval, so I can call this function rand and give it. I can request a number of random samples, and it returns me this random collection of intervals. What this function is essentially doing is it's randomly calling cut for random numbers on 0, 1. It's randomly just cutting the p-box. Okay, the other kind of interpretation is that now if I take a vertical cut of this p-box, an evaluation of its CDF, I now get an interval. So I can do that by calling CDF for some value. Right, and of course now when I ask for the probability that this variable is in some set, I no longer get a precise number, but I get an interval probability. And I can do that in PBA by calling by using this function mass for probability mass. I give it a p-box, and then I give it some interval that I want to know the probability mass on, and it returns me this interval probability. Okay, and p-boxes, they kind of generalize distributions and intervals in the following way. So if I start in the middle, and I start to remove distributions from this set by making this p-box more and more precise, I eventually end up with a single distribution function. And a distribution function is, in some senses, a p-box whose bounds are equal. And if I go the other direction, I start to reduce the stochasticity of this p-box. The distributions eventually become less and less, more and more scalar-like, and I end up with an integral. Okay, so how would you go about making one of these in PBA? Well, you can call a whole bunch of these parametric distributions, and by giving them interval parameters. So, for example, this one here is a normal distribution with an interval mean and interval variance. This is a normal distribution whose lower bound is an interval, a beta with interval parameters, and so on. Yeah, you can just essentially just call one of these parametric constructors and give them an interval for their parameters. We also have distribution-free constructors. So what these are okay, say you don't know that your variable is normally distributed or uniformly distributed, so on, but you have some information about the variable, such as its range, and maybe its mean and its variance. So the simplest one is an interval. If you just know its range, you know that the variable is in some interval. If you know its mean and its variance, you can construct a p-box which bounds all the distribution functions with those two properties. You can also use the mean on the lower bound, the mean on the upper bound. You can also use the mean on both the bounds, the range. You can also use the mean, the variance, and the range. And okay, for example, the way the constructors are as follows. So for mean and variance, you just call mean var. For the minimum and the maximum, you call mean and maximum, you call mean max. And for all three, you call min max, mean var, and so on. These constructors can also take interval parameters. Okay, this plot is just to show the kind of the variety of p-boxes you can get from knowing these 3 bits of information. For example, what this plot shows is I'm keeping the minimum, the maximum, and the mean the same, and I'm varying its standard deviation from 1 up to 50, where basically when the standard deviation is near 1, the p-box is pretty much precise, and when it's at 50, again, it's pretty much precise. And you can see the wide variety of p-box shapes you can get from these parameters. One of the most important features of this package is how we represent the distribution functions in p-boxes. So these CDFs are continuous and cannot be perfectly represented on the computer, which is discrete. But what we can do is we can create these coarser and coarser outer approximations of these continuous functions. So, for example, here you can see that I've made a 5-step representation of this continuous distribution function, and I get quite a coarse representation, but I can be sure that my continuous function lies within these boxes. So how do you do this? We have this function set steps, which you can do to essentially define the discretization of the probabilities. So 200 is the default. And now just to show you, essentially all distribution functions and p-boxes are p-boxes in here, so in this package. So essentially, even if I call this normal distribution with precise parameters, it's still a p-box and it still has an outer representation. So when I call CDF, I don't get a precise value, but I get an interval value, albeit that the interval is pretty small. Also the same for random sample of this precise distribution in PBA is going to give you an interval. Similarly for mass, it's going to give you an interval, and you can make the discretization more and more with higher fidelity by increasing this number, but and these intervals will shrink, but it's going to cost you computationally. All right, so I'm going to show you the arithmetic capabilities of this package. So we can do some bivariate operations, the ones that you expect, plus, minus, and so on. We can do transformations, univariate operations. This is a set-based package, so you can do some set operations with these p boxes, comparisons and logical operators. These are actually not yet implemented in the Julia version, but we know how to do them, and you can do stuff like sample and create stochastic mixtures. Just to show you what the univariate operations look like, so if I take this p box x, what you're seeing here is a whole bunch of univariate transformations of this p box. I can do things as well, like do a binary operation between a precise distribution and an interval, and this will generally give you a p box. I can also do binary operations between p boxes, but there's one important detail, which is that you need to also know the probabilistic dependency, in some sense the correlation between these two p boxes to evaluate the operation. So I'm going to show you the sum of these two p boxes for a whole bunch of different dependencies. So you can see independent correlation 1, correlation -1. Interestingly, gives you an interval back. It's not always the case. It just sometimes depends. Well, it depends generally on the shape of the two input p boxes. You can evaluate it for any arbitrary correlation. We can also do partially known or unknown correlations. So for example, here I'm showing you the sum for an interval correlation. I know that the correlation is positive. I can still evaluate the sum. I can even do things like if I have no idea what the dependency is, I can still do operations in terms of I can still do operations even without knowing what the dependency is. All right, just to talk to you a little bit about the multivariate case, the dependency capabilities of this package. So one thing to know is that correlation can only tell you so much. It's a pretty bad model for dependency, actually. What's shown here is a whole bunch of data sets which have the same correlation, but they're dramatically different. Here's something else. These guys, what they're doing is they're keeping the moments in the correlation fixed except for the last few digits, and what they can do is they can make these quite dramatically different data sets. So what we need is we need a model of dependence, which is not correlation. And what that model is copulas. What they do is you can basically encode any possible dependence you like exactly in a copula. What are these things? What they are? They're two-dimensional CDFs with uniform margins. Okay, so they're these CDFs which exist on the unit cube, and they generalize the notion of dependence. So, for example, independence is captured by this pi copula, which is just the product. And its CDF looks like this, and its density is simply just a flat on that square. And what copulas do is they couple distributions together. So you can give this function two univariate CDFs, and what it spits out is the bivariate version with the correct dependence. Okay, so in PVA, what I can essentially do is I can make two univariate p boxes, and essentially I can make a copula. For example, here is a Gaussian copula, and we have a whole bunch of different parametric copulas, and I just give this copula two univariate p box in the same sense of that Sklar's theorem I showed you, and I can now evaluate things like the bivariate CDF at some point. It gives me an interval. I can also evaluate the mass on some two-dimensional square, and I get the probability mass and so on. I can also take samples of these bivariate p boxes, and what I essentially end up with is this random collection of intervals whose marginals, sort of when you project them onto the axes, you get the p boxes back, and they follow this correlation that's encoded in the copula. Okay, I just want to show you, talk to you about this upcoming package that we're working on with Marcelo, Christian, Lewis, and Scott. It's called probabilistic reachability. What it essentially does is it combines this package I've been talking about, probability balance analysis and reachability analysis. So, okay, what these guys in reachability can do, they can propagate these intervals or sets through ODEs in a really nice way. You can see that the set is represented by this kind of zonotope, which is like a set defined by linear constraints. And what we'd like to do is essentially, okay, instead of the initial condition being known to a set, but being distributed like a distribution or like a p-box. And what we can do is we can sort of propagate these p-boxes through the ODE, and then we can ask questions like, okay, so I have this future set here, which is going to be something bad. Maybe it's going to be like a system failure or something like this, and I'd like to know what the probability or interval probability is of this set occurring following that I know that the initial state is a p-box. And we can do that, and you essentially get interval probabilities back for this kind of thing. All right, so just to talk about the future work. So this package is not yet strictly rigorous. There's a couple of details that we need to sort out. The guys in Julia Intervals have put a lot of effort into ensuring that their package is rigorous. We haven't done that completely yet, but they've given us some really nice suggestions about how to do that. There's also another detail I've not really spoken about, which is, okay, in interval arithmetic you have this problem, this dependency problem. They call it the wrapping effect. But we have the same problem in this package here. But we are working on, we have some ideas of a solution to this. So this is called generally dependency tracking. Okay, there's also two other upcoming packages. So today I've shown you of p-boxes, but there is another representation of a set of distributions, which is a possibility theory, which is essentially fuzzy numbers for bounding sets of probabilities. There's also a logical version of this, which is essentially the same package but for Boolean operations, so like AND gates, OR gates, and so on. Okay, thank you very much.
Okay, well, thanks very much to Ander for a great talk. So we have a couple of questions. The first one is from Goran Frehse, who asked, to what extent are the distribution-free constructors tight? For example, for mean equals 0 and standard deviation equals 1.
Yeah, thanks for the question. I think they're best possible. So the mean and the variance p-box comes from the Chebyshev inequality from probability theory. And I think if you were to try and reduce the bounds, you'd actually become wrong. So I think they're best possible. The other sort of distribution-free constructors come from different inequalities from probability theory. I believe that's right.
Okay, great, thanks. Apologies, I seem to be having some trouble with my computer, of course. Okay, and there's a question from YouTube, which is, can you use phase spaces to bound otherwise apparently infinite constraints? E.g., sine of x appears infinite in the time domain, while FFT of x, the fast Fourier transform, obviously finite. Not quite sure exactly what that means, since we don't exactly have the time domain here, I think. But I actually had a related question, which was whether you are actually bounding these distributions out all the way to infinity.
Yeah, so if the distribution function has an infinite support, it is a little bit tricky. But
right,
essentially,
the box has infinite volume.
Yeah, essentially what you have to do, yeah, you cut the way you do this out of discretization, you don't do it from 0 to 1. You define like a lower limit, like 0.001 or 0.999, blah, blah. And then you slice it like that there. And if you query something outside of that box, you just return the last known value, and you're actually still able to bound you're still able to bound the probabilistic quantities correctly.
Okay, great. Any more questions from the from the speakers, panelists? I don't see any more questions. Okay, and so I mean the same question as usual. To what extent can you go to higher dimensions? always the issue with these systems.
Yeah, it's pretty it's difficult. I mean, we have this wrapping effect, and it's really
right.
Just like with intervals, that the more dimensions you go and the more repeated variables you have, your answers are going to get fatter and fatter. You're still going to be rigorous, but you're just not going to be tight. So
right.
The aim of the game is, okay, can I actually make my answers tighter and tighter with more computational effort, and what's the correct way to do this? This is the kind of the burning question that we want to answer. Yeah.
I mean, GPUs is maybe the answer.
Yeah, parallelism.
Yeah. So there's actually a question from LinkedIn. What about the Shine and Cosh hyperbolic functions? Have you implemented those?
Okay, so yeah, essentially, we kind of piggyback off your interval arithmetic package. If you can propagate an interval through it, I can propagate a p-box essentially.
Oh, great. Okay, so apparently the answer is yes, we can do those. But what is much harder are the sort of special functions like Bessel functions and things. Somebody has to sit down and implement all of those for interval arithmetic, and that's actually a hard task that I'm not going to do. So if anybody is interested, please feel free. Okay, thanks a lot again for a nice talk, and let's move on to the next session.
Thanks.
Okay, so the next talk is by Jorge Perez, who's a professor at the Structures Department of the School of Engineering at the Universidad de la República in Uruguay. So let me add him to the stream. Hi, Jorge.
Hi, how are you, David?
Good, thanks. How are you? So I'm going to share your talk, and then we'll have the questions afterwards. So this is, sorry, too many windows. I lost the window where I had the, there we go. So this is about using set propagation and the finite element method for time integration in transient solid mechanics problems by Jorge, together with Marcelo Forets, the organizer, and Daniel Freire Caporale. Okay, they're all from Uruguay. Okay. So now,
the objective of this platform is to control complex dynamical systems such as a drone.
This it's a very confusing interface. Sorry.
It's fine.
There we go.
Hello, my name is Jorge Perez, and I will present an application of set propagation and finite element methods to transient problems in solid mechanics. This work was developed with Marcelo Forets and Daniel Freire Caporale, working at Universidad de la República in Uruguay, with the financial support of Comisión Sectorial de Investigación Científica and Agencia Nacional de Investigación y Innovación. I will start with a brief introduction to the problem and present some preliminary concepts. Then I will describe the method developed, present the numerical results, and enumerate the conclusions. Transient problems are those with state variables that change in time. In solid mechanics, we can find several of these problems, such as heat transfer and wave propagation. The resolution is required in different relevant applications, such as wind energy production, design of massive structures, or even simulating the effects of COVID-19. The numerical resolution of these problems is a challenging task, and new methods keep being developed. Moreover, real-world problems include uncertainty in parameters and input sources, and the common approach is to simulate and test, which becomes computationally intractable in verification problems. Our goal is to develop new resolution methods for input sources with uncertainties. Our approach is to combine two methods. On the one hand, the gold standard method for PDE domain discretization, and on the other hand, an innovative approach for ODE's resolution. Let me present the idea behind the finite element method. To do so, I will consider this simple problem given by a solid with a stiff circular inclusion with two fixed points and a known applied pressure P variable in time. The continuum dynamics problem consists in finding for each time t the displacement field U solution of the partial differential equation 1. The finite element method divides the domain into elements and considers the balance equations for the discretized domain. The problem is then converted to this, where the continuum domain was discretized into a mesh of triangular elements with 600 nodes using the GMSH measure in this case. The displacement inside each element is interpolated using the nodal displacement values. The partial differential equation is now a system of 1.2 thousand ordinary differential equations, and the vector capital U contains the displacements x and y of the nodes of the mesh. The differential equations for general linear heat transfer or structural dynamics problems have these expressions, and both have standard numerical integration methods commonly used. The most relevant methods are shown here, in which the time domain is discretized and the balance equations are imposed at certain time steps. These methods are implemented in the library called ONSAS, which is an under-development open source tool for nonlinear structural analysis. It can import GMSH mesh files and write BTK files. At onsas.org, you can browse the current version of the documentation and the code. This is the tool that will be used in this work. In this particular example, we can use ONSAS to solve the problem and obtain this plot of the magnitudes of the displacements. The load applied is an impact pressure, and we can observe that since the inclusion is stiffer, the wave propagates at a higher speed on the left region as expected. Now, let us introduce the ideas behind set propagation methods. As we said, when uncertainty is present in the input sources, the simulation approach becomes intractable. A prominent framework used to solve verification problems consists in using unions of sets to cover all the exact solution of a dynamical systems for all the initial states and all admissible inputs and parameters. Such approach is called reachability analysis. The methodology we are proposing might enable the development of new applications in engineering problems. This approach is implemented in tools such as Julia Reach, a library focused in the development of efficient methods for reachability analysis and related computational problems. It is implemented in Julia and is also hosted in GitHub with extensive documentation available. This is the tool used in this work for reachability analysis. Now I will describe the methodology developed. The method consists in 3 steps. First, the differential equation system is converted into an homogeneous and first-order form. Then a set omega 0 containing the trajectories of all the exact solutions between 0 and delta is constructed. And finally, that set is propagated for the following times using the state transition matrix. To present the steps of the method, I will use a simple example, a single degree of freedom problem, which can describe a spring mass system. 2 cases for initial conditions are considered, a single condition and a hyperrectangle set. For the spring mass problem, the first step of the method consists in the order reduction. Then, defining the variable x, we obtain an equivalent formulation as a system of 2 differential equations of first order. For the second step, in the single initial condition case, we show here the phase space. The green circle is the initial condition, the yellow circle is the analytical solution at time delta, and the set omega 0, as we can see, includes the analytical solution. For the case of a set of initial conditions, we can see that the analytic solutions are included in the set omega 0 as well. In the last step of the method, the set omega 0 is propagated for each following time interval, and the obtained sets can be represented using different set representation strategies with different levels of accuracy and computational costs. In the case of a set of initial conditions, the propagated sets also include all the trajectories of the exact solutions of the system. Here we can see a plot of the displacement and in time for the first seconds. Here are the displacements after 2 periods of time of simulation, and we can see that the set-based method provides more accurate solutions than the standard numerical methods. Let us now see the numerical results obtained. To show the results regarding the accuracy of the method, we consider a unidimensional wave propagation problem from the cited reference. The domain consists of a bar clamped on the left and submitted to a step force on the right. The problem is governed by the partial differential equation 8. The continuum domain problem has an analytic solution shown in equation 9. The domain is discretized using 1000 elements, and we obtain this reduced stiffness and mass matrices. No damping matrix is considered in this case. The nodes are numbered from left to right. The displacements obtained for node 700 are shown here, and we can see the peaks which show the time when the wave is passing through the node. Here we can see a zoom of the plot where the flow pipe with the set solutions is more accurate than the numerical integration methods. Here we see the velocity at node 700. And once again, we see the zoom showing the higher accuracy of the set-based method. In the following problem, we solve a realistic model for concrete casting heat of hydration. The problem is motivated by the design process of massive concrete structures. Maximum temperatures during curing must be safely estimated in order to avoid cracks developed in the structure. Given the symmetry of this problem, a quarter of the domain is meshed and analyzed using ounces. These are the parameters considered. And the external temperature is assumed to have a sinusoidal variation, and the heat of hydration is modeling using an exponential law. Using a fixed parameters set, we obtain these plots for the temperature distribution and these temperature evolutions for the control points. We can see that numerical methods provide slightly lower values of temperature around 51 hours. As expected, the temperature closer to the center of the massive piece of concrete is higher than the control point closer to the frontier of the domain. Considering variations in the level of heat and the external temperature, we obtain these plots, which provide a key result for safe design and verification of these kind of structures. We can conclude that this combination of methods is a promising tool in engineering verification problems. The method provides accurate solutions compared to reference numerical methods, and the method allows to obtain solutions for distributed initial conditions. Several work lines are opened, including parameter uncertainty, extensions to nonlinear analysis, and considering probability distributions in the initial states. These are the references cited. And thank you for your attention.
Well, thanks, Jorge, for a very nice talk.
Thank you.
There were a couple of questions on Discord from myself. I was wondering, are these methods rigorous? Are they guaranteed to give you the correct result? And as part of that, how do you bound the solution of your ordinary differential equations?
So I understand that you're asking about the methods proposed. the set propagation methods.
Yes.
So since, that is more like the reachability analysis theoretical aspect. One of the articles that I cited is the archive article. So in that one, we proved two propositions which provided some theoretical results for having a certain coverage or convergence about the bounding of the solution in relation to the time increment. So if we reduce the time increment, then the boxes converge to the analytical solution. And also, I think that's more or less of it. I am in the finite element method side of the presentation, so maybe Marcelo can join if he wants.
I think it's very interesting that you're saying that these set propagation methods are better than the standard numerical methods. I think that's already a very, very interesting point, even if they're not guaranteed or rigorous.
I mean, yes, and I mean we do not have not seen any previous result about this combination. I mean, this was not yet done. Maybe some smaller examples or specific applications in heat transfer, but in this publication, in this presentation, we are showing for the first time a finite element method formulation in variational formulation mixed with set propagation. So so there is still a lot of work to be done. And indeed, in fact, the set propagation method is better if you compare, for instance, in cases where you have a set of initial conditions, and if you want to verify some condition for all the initial conditions in that set, then the numerical integration methods are required to perform a large number of simulations.
Right.
In that case, this set propagation method is, of course, much better and much more efficient.
Great, thanks. There's also a question from LinkedIn, which was, why is Julia better for FEM, the finite element method, and CFD, computational fluid dynamics, than Python? That was the question from LinkedIn.
I mean, so as you saw, the ONSAS package, the ONSAS library that we are very recently developing with our colleagues, Bruno Bassano, Mauricio Ansuri, Marcelo, and some Joaquin, a few colleagues from Uruguay, and also colleagues from Sweden and Argentina. So we started using Octave. It's a MATLAB Octave package library, but as I posted in the Discord chat, we are starting the migration to Julia. So I won't get into the discussion about which is better, because I am not the one to say that. I'm not an expert. I am just a humble developer, an engineer. So yeah, by the moment we are in Octave, but you can run this in MATLAB. But yeah, we are switching to Julia because it's such an interesting develop to do.
Great, thanks. Yeah, that's a very that's a very good question, and it's one which we don't have time to cover right now. So,
of course.
Please, if you have that question, do feel free to ask it on the Discord chat, or there's plenty of discussion about it on the Julia Discourse, which is this online forum. Okay, so I think we have to move on to our next talk. So thanks again, Jorge.
Okay. Oh, thank you.
Okay, so the next talk is going to be, I believe, Solving Optimization Problems with Embedded Dynamical Systems by Matthew Wilhelm. And Matthew is a PhD student at the University of Connecticut in the USA. So let me add Matthew. Hello.
Hello.
Welcome. So I'm going to play your video.
All right, sounds great.
Yeah, it's very confusing. No.
Hello.
Let's try again. Here we go. Okay.
I'm Matt Wilhelm, a fifth-year PhD candidate at the University of Connecticut, working with Professor Stuber. It's my pleasure to discuss some of the recent work we've done solving optimization problems with embedded dynamical systems. Now, the particular class of optimization algorithm I'll be focusing on today is that of deterministic global optimizers. That is, when these algorithms terminate, they furnish a solution which is known to be the true global optima of the function within specified user tolerances. This approach is particularly useful for many distinct classes of problems. So we have the traditional non-convex formulations, such as the mixing and pooling problem, where we may have a large number of non-convex and non-convex equality constraints in particular for this case, which result in there being many local optima, and by operating this mixing and pooling operation at a global solution, you can achieve some particular economic benefits that may be quite substantial compared to using a local solution for this problem. In other cases, such as the design of safety critical systems, the information you get from a global optimization scheme may be qualitatively better in informing design decisions than local optima. So if I have the mixer and separator system here, wherein I have heated pressurized vessels, well, it's very useful to know what the highest attainable temperature in the system is in terms of information that will help me pick materials of construction and also specify safety equipment. Knowing a suboptimal high temperature doesn't necessarily inform my decision the same way when building that. Lastly, there are a number of cases where the configuration of a physical system is defined by some sort of optimization problem. This occurs in thermodynamics, where I might be defining equilibrium as a minimum of Gibbs free energy. And we know these systems explore the underlying space so efficiently that we're never actually going to encounter a suboptimal point in any, hundreds of thousands of universe lifetimes. So really the true globally optimal stable solution is what determines the configuration of our system. Now, essentially all these optimizers work on some variation of spatial branch and bound. So essentially you have a stack of nodes which defines the domain of the problem. You pick one of those nodes, you compute a lower bound, you compute an upper bound. If your lower bound is worse than a candidate upper bound in some other region, you can discard the region you're currently looking at because you know it's the best possible solution is dominated by a candidate solution in some other region. And you keep partitioning these nodes and you keep computing lower and upper bounds. And if you do this with some mild assumptions, eventually you get to a true global optimal value. Now, the focus of this talk will be really how we've done some recent work on integrating ways of constructing relaxations and bounds of dynamic systems into this general global optimization framework. So there are two classes of algorithms that are generally used to construct these types of relaxations of dynamic systems. There's the discretize and relax approach, in which you discretize the problem into a finite number of time points. Then you construct relaxation at each of those points in time. And that's what we've done some initial work in this area where we've developed specialized implicit multi-step methods, and that in part is motivating some of our interest in these global optimization problems. There's also this other class, which is generally referred to as this relax then discretize approach, wherein the relaxations of the dynamic system are defined by an auxiliary system of differential equations, which you can then just integrate using modern differential equation solution methods. So you can think sundials, you can think ODE45S, most sort of algorithms that you can access through differential equations, Jodel would be adequate for solving these types of systems. So to take that dynamic relaxation algorithm and incorporate it into a global optimizer, it enters play mostly in construction of lower bounding problems and in domain reduction. So we need to take our active node, we use this algorithm to compute relaxations of the state variables at a certain number of points. Then we apply a McCormick-Othberg arithmetic to compose these relaxations in a way to get the objective functions, relaxations, and the relaxations of constraints needed to solve a lower bounding problem. Generally, we have three main options for this. So we can use that algorithm we've just talked about, and that defines a single evaluation of this convex relaxation. And we can solve a convex nonlinear program by repeatedly evaluating these, getting great information, solving linear systems, the whole shebang. We can also take our relaxation, evaluate at few particular points, and since it's convex, we can generate certain supporting hyperplanes and use these to define polyhedral relaxations of the convex relaxations, solve these via a linear program. We can also refine interval bounds because the interval extensions of these supporting planes can be used to define valid interval bounds as well. And you can intersect these with natural interval bounds to get something that's necessarily at least as tight and often tighter. And which of these you choose is basically dependent on the problem structure, whether it's prone to sort of numerically stable intermediate calculations, or also whether you can effectively solve a nonlinear program quickly, because if you can't, maybe it's worth solving a linear program which is less tight, but solving it much quickly and transversing the branch and bound tree more efficiently. Additionally, for domain reduction, we can solve optimization problems to shrink the domain. So instead of having an objective which defines this minimum of the objective function we're looking at, we can specify that we'd like to instead maximize in the p direction, and if we get a value that's smaller than our initial box size, we can infer that there's some infeasible region we can cut off. So to actually use these, we need to be able to query the convex and concave relaxations we've calculated, the subgradient or gradient thereof, interval bounds, and also to infer some status related to the relaxation algorithm. It's possible that in some cases these won't necessarily terminate adequately. So we just need to know that so we can throw it to a different backup routine if necessary. Now, the upper bounding problem is generally much simpler for global optimization. Essentially, all we really need to do is compute a feasible point. So typically what's done is you solve a nonlinear program to local optimality. In some cases, you'll set up acceptable tolerances and limits in case to limit this from going too far or to spend too much time on a single local NLP solve. And then to do this, we use the same usual toolbox of things you need for solving locally nonlinear programs. So that would be evaluating the objective, constraints, gradients, Jacobians, Hessians, possibly some vector products if you want to be efficient about storage and memory consumption. So we tried implementing this in Ego, which is our global solver we've been developing in Julia for quite some time. It's meant to be extensible, and we've applied it to a number of fairly exotic optimization formulations with somewhat novel solution methods that we probably couldn't do using off-the-shelf global optimizers that really focus on standard factorable functions. Well, you run into a couple problems when you initially try this. First, you need really highly performant code to evaluate the trajectories of differential equations, because we may be evaluating millions of these trajectories to solve these nonlinear optimization problems or the millions of lower bounding problems we may eventually go through. Additionally, this may be kind of obvious to some people, but the state variables that are used to define these dynamic problems behave differently than the decision variables in typical optimization formulations. That is, they're parameterized by the decision variable usually and time, and that introduces some complexity in how you actually query information relating to these variables. So we've built a couple of these packages which contain various discrete and continuous time approaches for relaxations. We also included this abstraction layer to essentially give us a standardized means of defining problems and querying them that is separate from the core global optimization functionality. We've done this by essentially creating two classes of structures. So there's the abstract relaxation problem, and then there's an abstract integrator. So the relaxation problem holds all the relevant mathematical information you'd need to have a well-posed relaxation constructed via some method. And then to this problem, we can add various information if we're going to use that to refine the relaxations via a get and set functionality. We take this problem, we build the integrator, and we can again set. So what this looks like in Julia is we have this system of parametric differential equations as one example. So this is just a differential equation system where we have some parameter values p. There's an initial condition, which in this case we fixed to a fixed number of concentration values. And then we know that the kinetic parameters vary within some predetermined box. So we set this up in many ways like we would a differential equation that we've defined with, say, differential equations at JL, where we have a right-hand side function, we have initial conditions, we have a time span, and then we associate with this again a box over which we can actually compute these relaxations and build our relaxation problem. Now, in this particular case, the example was drawn from the chemical kinetic world. And we know that for these types of problems, we can incorporate some additional information to potentially tighten the relaxation we end up getting using our algorithm. So one thing that's useful here is to go back to your high school stoichiometry and realize that in this system, we're not creating and destroying mass. So we can take our chemical equations and make a stoichiometric matrix, and that defines this linear system which must be satisfied. We also know that the concentrations have to be below some sort of maximal value for typical temperature and pressure in this little liquid vessel. So we can also associate some upper and lower bounds for the state variable, which we know a priori. And we do this, again, using the get set functionality as shown here with some particular attributes. We then build our integrator. In this case, this is a relax then discretize approach. We specify a parameter value to evaluate the relaxation at. Then we relax the problem and query attributes. We can do this either using essentially integer values to grab the third or fourth, or the bounds at the third or fourth point rather, And we can also specify that we'd like information pertaining to a particular time point via floating point number. So what happens at time 0.025. Additionally, we can integrate the problem at particular parameter value and not compute a relaxation, but rather get a local trajectory and gradient information thereof. We've chosen to associate each of the relaxation algorithms with an integration scheme. This is because we want to be able to support relaxation approaches that don't necessarily rigorously account for truncation error. So we can associate a local integrator that has the same truncation error properties and avoid falsely fathoming things in global optimization via that approach. So just to look at how this integrates in with Eco's overall functionality of solving fairly complex script-defined optimization problems. We're going to look at this exothermic polymerization reactor example, where we're really considering whether once this reaction is going, it hits its peak temperature, if a sensor were to fault, would that sensor fault essentially throw us outside the realm of a controllable system at that particular time step. So we can formulate this as a robust operation SIP. Again, it embeds this dynamical system, which is just going to be a mass and energy balance associated with that chemical reacting system. The actual rates, though, get kind of complicated in that you have to solve this nonlinear system of equations to find a quasi-steady state. So we've replaced this with a surrogate 3-layer Gaussian error linear unit feed-forward neural network to approximate this nonlinear solve. And then when we apply a modification to the SIP res algorithm in Ego, we can solve this in under a minute. We're fairly excited about extending this approach to other somewhat weird classes of functions that aren't really in the standard global optimization factorable function framework for modeling. So one of which is implicitly defined functions that are defined by some sort of nonlinear inequality constraint. Neural networks are a great one that we're going to be looking at further in the future. And more recently, there's been some work on bounding distributional properties of continuous random variables, as well as constructing convex concave relaxations of actual black box functions effectively. And we think that this type of approach, because it falls in this generalized McCormick framework, is something we can compose with other types of differential equation solving approaches, stochastic differential equations, etc., to generate some new theory and approaches. So we're excited about that. We'll also be looking at integrating this further into Ego and extending this to support additional Julia-based functionalities, such as tailormodels.jl through wrappers. And yeah, I'd just like to thank the University of Connecticut National Science Foundation for funding. Thanks. Bye.
Well, thanks, Matthew, for a very nice talk. So we have had a few questions going on the Discord. So Chris Rakorkas asked, "What's the largest problem you've tried Ego on?" I actually thought it was pronounced Iago, so I learned that it's pronounced.
Yeah, I think it's up in the air a little bit depending on however you choose. But yeah, so generally for the non-convex programs, what we're looking at is how many variables are participating in these nonlinear, non-convex terms. We can run linear problems that are in the tens of thousands, 100,000s, no big deal. But generally, we've solved some with 100 nonlinear, non-convex participating variables, and it does better with 10 if you have very complex expressions. We are subject to the wrapping effect that you get from normal arithmetic or other composite terms. So,
yeah. And yeah, I asked, why is it that, as far as I understand, your approach is based on McCormick relaxation, so these convex and concave overestimates or underestimates of a function. And I was asking why is that a good approach, basically, compared to interval arithmetic, say?
Yeah, so in many applications, you can find some corner points where this isn't true, but you'll recover relaxations which are much tighter than the actual interval bounds because the dependency issue when you compute relaxations isn't as present.
Okay.
And in many cases for small functional terms, you actually will recover the envelope of the underlying function. So you have the best possible estimate that is convex, which is the easy problem form to solve with a subsolver.
So what subsolver do you use for that?
Right now, we're actually taking that convex envelope and then using a subgradient to construct a lower bounding plane at a few points, doing this polyhedral relaxation approach. And then we feed it to either CPLEX, GLPK, just a general linear solver. You can also use a nonlinear solver, but it's generally not as quick for global optimization because you still might have a lot of overestimation of the function, and finding the exact min that's a little bit tighter for this relaxation might not save you much.
Okay, thanks. So we just had a question from Fleming concerning optimal control problems. Have you started thinking about how to do the branching on infinite dimensional spaces?
Short answer would probably be no. We've done some semi-infinite optimization algorithms where we have restriction-based approaches to that, but branching into infinite dimensional spaces is something we just haven't looked at.
Okay, thanks. Okay, I think we should move on to the last talk. So thanks again to Matthew.
All right, thanks.
And so the final talk of the session is going to be Methods to Soundly Verify Deep Neural Networks by Tomer Arnon. And Tomer is a PhD student at the Stanford Intelligent Systems Laboratory. So let me add Tomer to the thing. Is that the right way to say your name?
Yeah, Tomer. That's
okay,
right.
Great. Okay, I'm going to play your video. Here we go.
Arnon, and I'll be talking about formal verification neural networks and a package called neuralverification.jl. Neural networks are general function approximators, and they're used in a wide variety of applications spanning from computer vision to robotic control, and in particular in domains that are traditionally difficult for computers. Although the networks are built up of simple building blocks, because of their complicated structure, it can be very difficult to prove certain input-output properties hold on these networks. And we'd like to be able to do this, especially as these networks occupy a greater role in critical applications. I would like to mention that the field of neural verification is quite new. The first sound and complete method, I'll mention what those mean in a moment, was published only about 4 years ago. Neuralverification.jl is a Julia package with 18 sound algorithms implemented. It accompanies a survey that we conducted that covers these methods. And I'd like to say, since this is JuliaCon, that rather than use pseudocode in that survey, oftentimes we use the Julia code unaltered in its place, which is kind of neat. So a bit about the survey. Our goal was to introduce a unified mathematical framework for this problem and to taxonomize the approaches, to figure out how they relate to one another and how this field is growing in different directions. We also wanted to approach the algorithms pedagogically. We wanted this to be a pedagogical tool, ultimately, and to help open up the field. This is just a snippet from the GitHub page of the package. Okay, so briefly, what is a neural network? A neural network is made up of a series of layers. Each layer has a linear step represented by a series of weights and biases, and a nonlinear step. The nonlinear step in our case is usually ReLU, called the rectified linear unit is what that stands for, and all it does is it sets negative values to 0, and that's it. For the sake of notation, I'll also mention we call the input to the network always x, the output is always y, and the internal state if you will, of the network that's being passed from layer to layer, we call Z hat prior to activation and Z post-activation. Okay, now what is verification? This is the verification problem here. For all x in some input set x, y, meaning f of x, f being the neural network, must lie in some output set y. We can imagine this in the context of image classification by saying for some radius in image space around a particular image, we would like the label not to change. We've all seen this sort of example where some small perturbation will vastly throw off a classification network. And we'd like to be able to show formally that for a particular network, perhaps even a particular image or set of images, that isn't possible. We can also imagine this in the context of a safety critical system. For example, maneuvering an airplane. And we'd like certain nonsensical outputs to be impossible in given situations. For example, here where the intruder is on the left, we would like to be able to prove formally that the network will never output the direction left, that the plane should turn left. We can imagine that if it was possible for it to do that, that could be disastrous. Okay, so why don't we just sample a lot of points and call it a day. The problem with doing this is that neural networks are very spiky, as we can see here. And so this kind of statistical validation is brittle. We would like to be able to prove in many of these safety critical systems that something is impossible, truly impossible, not just statistically unlikely. So, briefly, I mentioned soundness and completeness. I'll just define them. Soundness means that there are no false negatives. It means that your algorithm will never tell you that the network is safe, if those are the terms that we're using, if it's unsafe. Completeness means that there are no false positives. So the network will never be, the algorithm will never tell you the network is unsafe if it is in fact safe. We chose to explore algorithms that err on the side of caution, which means we would rather have false positives than false negatives. There are three basic ways that a network can fail the verification test. The first is that we find a counterexample. We find some point in the input set, that maps to a point in the output space that is not in the output set, and therefore the property is violated. In other cases, we can find a radius in the input set, we can map the output set backwards and find that there is a radius in the input set which violates the property. Finally, and this is the one we'll focus on, is we can forward propagate the input set as a set, not as a series of points, through the network, and determine whether that reachable set ultimately lies in the allowed set. In this case, it doesn't, and therefore the network has failed the property, or the property is violated, is what we say. There's also three basic approaches we can take to do this. We can use reachability, we can use optimization, and we can augment these two with search strategy. And we'll look mostly at reachability, but I will mention a bit about optimization as well. Okay, so how does reachability work? Well, we have our input set. We perform a linear transformation on an affine map, meaning rotation, scaling, and translation. And we can do that with the weights and biases. We get z hats from that. Then we do the nonlinear step, which is the complicated piece of the operation. For ReLU, what ReLU does is it projects the negative portions of the set onto the axis. Here, it may be hard to tell, but there's actually a little tail right here from this set. We repeat these operations throughout each layer until we encounter the ultimate reachable set here. There is a problem with doing exact reachability, as we showed before, which is that the number of sets that you need to keep track of grows potentially exponentially with each layer. Every time you project, you end up with these sort of, or you can end up with these sort of tails. And because this is no longer a convex set, you have to represent it as the union of sets, and you have to keep track of each member of that union separately. The worst case complexity of this becomes 2 to the n, where n is the number of nodes in the network. Since these networks are very, very large, that is entirely untenable. So what do? One approach we can take is split and join. So every time we split and then project these sets to get this, we then join them again, over approximating them with some other set, and now we're back to 1. Now we only have to keep track of a single set, but the price we paid is over approximation. We no longer have a complete algorithm, although it is still sound. Another thing we can do is we can use interval arithmetic to over-approximate earlier in the operation. So here, after the rotation, we over-approximate here, which makes the projection step very cheap. But again, the price that we pay is over-approximation. Another thing we can do to try to minimize this over-approximation is we can propagate through the network a symbolic interval, a symbolic input, rather than a concrete interval with concrete values, and hope that certain cancellations take place that will minimize the over-approximation. Here we see an example, a trivial example of that. And in practice, the various algorithms use a combination of these techniques. Okay, I want to look at a case study from the reachability algorithms called AI squared. AI squared employs split and join. And the original AI squared paper described several domains that AI squared can work on. Abstract domains is what they call them, which is a geometric template that is used to perform the over-approximation. You can use a hyperrectangle as the over-approximating shape, which is very cheap to do, therefore very scalable, but also very over-approximate. You can use a zonotope, which is a shape that is symmetric with respect to a set of basis vectors, but the basis vectors are arbitrary, so it is more general than a hyperrectangle, still relatively cheap, still over-approximate though. Or you can take the convex hull, essentially, of the union of shapes that we saw before, ending up with a general polytope, which is the most precise. It is still an over-approximation, but it's more precise, but it scales more poorly in higher dimensions. So, I'd like to show what this looks like to implement AI squared in Julia. And this is taken straight out of neuralverification.jl. So the first thing we need is some generic reachability tools to be able to do this. We have to know how to push a set through a network. And the way that we do that is that we loop over each layer in the network, and we call forward layer with the input set and each layer. And the output here, Z, of each layer becomes the input to the next layer. So we just keep overwriting Z. Forward layer consists of two steps: the linear step, which produces
Can you see me? Sorry about that. My browser crashed. Let me try to share again.
My name is Tomer Arnon, and I'll be talking about formal verification of neural networks and a package called neuralverification.jl. Neural networks are for over-approximate abstract domains, is what they call them, which is a geometric template that is used, still relatively cheap. So we have to know how to push a layer, and the output activation step, which produces Z, and we return them both. In this case, we only care about Z. The last thing that we need is a way to check whether the reachable set lies in the allowed output set, and we just use is subset straight out of lazy sets for that. Okay. So now that we have this, we can define our AI squared. The solve step of AI squared will be fairly trivial. You compute the reachable set using forward network, and then you check the inclusion of that reachable set. So now all we need is to define a forward linear set and a forward act step, which is the activation function. How do we do those two operations? So for the zonotope domain, it's quite simple, as you see, two one-liners. The linear step is an affine map straight out of lazy sets, and the activation step is to over-approximate the rectification, which is another word for ReLU, and we over-approximate as a zonotope. Both of these straight out of lazy sets. And that's it. This is the zonotope domain of AI squared. And with a bit of multiple dispatch, we can also define the hyperrectangle and H polytope versions, or the polytope versions of AI squared just as easily. And so you see this is the entire algorithm of AI squared implemented in just a couple of slides. I will mention we use the concrete operations such as affine, map, rectify, etc. There is room for laziness to use the lazier operations found in lazy sets, but we don't do that here. There is some room for optimization doing that. Okay. Another case study, at least a partial case study that we'll see, is ReLUval, which uses iterative interval refinement. The way that it works is that you take your you start with your input set, and you propagate it through the network using reachability in a very over-approximate way, something that's very fast and cheap. And you end up here, because it's so over-approximate, you don't know if you're violating the property or not. You just know that it's not in the output set, so it should violate. So what you do is you split. You find the interval, you split it in half, find the left side holds, the right side is still violated. So of course you split again, this time top and bottom. We find that this half holds, we find that this half holds. Every time you split, the over-approximation decreases. And so using this sort of strategy, we can reduce the complexity of the computations that we have to do, while still keeping these relatively precise as we refine. I did want to mention on this slide, on these slides, as I mentioned before, we use Julia code as a stand-in for pseudocode in the paper, and so you can see here just how simple and how this would be no clearer if we were to use pseudocode. It's as good as it gets practically. So we use code almost identical to this in the survey. We'll look at ReLUval for just a moment. We won't go through it the way we did with AI squared, but I just want to point out that the algorithm we just saw visually is still very discernible here. You have some list of intervals of sets. You take an interval, propagate it through the network, check inclusion of that reachable set, and if it is unknown, if the result is unknown, you bisect the interval. In this case, it uses this value called the smear, which is described in the initial ReLUval paper. What it is exactly is not important, but I do promise it is readable Julia code all the way down. Okay, I do also want to briefly mention how the optimization approaches work, which is that we define an optimization problem with some objective and the constraints that x must lie in the input set x, y must not lie in the output set y, so we're in search of counterexamples, and yet y is f of x. So if all these three constraints hold simultaneously, we have found a counterexample. And we can define this as a feasibility problem with no objective, or we can use the objective to help guide our search. This in particular here, y equals f of x, is quite tricky to define. And the reason is that ReLU is a nonlinear, non-convex operation. So what we tend to do is relax it in some way, either this triangular relaxation, which is convex, or as parallel relaxation, also convex, or we could use a mixed integer encoding to switch off which branch of the ReLU we are in. And the different algorithms use different approaches in terms of what encoding to use, and they trade off precision and scalability and so on. Okay, another quick case study here is we'll look at NS-verify, which is sound and complete and also intractable in most cases, as sound and complete methods tend to be. Not always though. And it defines it's a feasibility problem. It defines the constraints x and x, y not and y equals f of x, and in search of counterexamples. It uses a mixed integer linear program. We won't go through the code. The one thing I do want to mention is that we use lazy sets in conjunction with jump for the optimization methods. And so for example here, this function add set constraint internally looks like this. And this is taken straight out of the library. It's exactly what it looks like. And we use too simple hrep, for example, here to constrain z to lie within that set. So add set constraint on a particular set will constrain the variable z, the input variable in this case. This is the first variable to lie in the set that we'd like. And so you, again, multiple dispatch along with the functionality in lazy sets makes this just endlessly expressive and makes the code very readable, very simple, very modular. Okay, I think that's all I'll have time for. So I wanted to wrap up and say that what we set out to do with this project was to create an entry point, a reference tool, and also to provide insight with these various methods, how they fit together. We also wanted to create a pedagogical tool. That's what we wanted this to be used for. And we know that it has been in a couple of instances, for example, a workshop that was led at Stanford, and also as part of a course at CMU called Provably Safe Robotics, taught by Professor Liu, who spearheaded this survey, who is the first author. I also wanted to mention before wrapping up some open problems in the field. There are still many. We have to generalize to more general networks. We pretty much only deal with feed-forward, fully connected networks with piecewise linear activations, and anything that deviates from that is very difficult, very hard to deal with at the moment. We also have a problem with scalability. Real networks are very large, and they're only getting bigger. And these methods really can't deal yet with any practical real-world networks, almost at all. Some smaller networks, they can. We also have a problem with expressiveness. The kinds of properties that we can define in terms of these input-output sets are quite limited. We'd like to be able to say things and prove things about the set of all cat photos or the set of all safe actions, but we don't even know how to describe these things, and they may be impossible to describe. But certainly some work needs to take place in terms of this expressiveness and what we'd like to prove. I'll go ahead and skip the conclusion slide and put up this acknowledgement slide. There are plenty of people to acknowledge the CARS Institute at Stanford, all of the authors of the original papers we cited in our survey, and of course, in particular, Marcelo and Christian for organizing this mini-symposium, for inviting me to speak at this mini-symposium, and for their ongoing implementation support throughout the project. I'd also like to thank my advisor at Stanford, Professor Kokendorfer, and also Professor Liu. Since there's no room for questions in this format, here's my contact info. Feel free to get in touch. Thank you, and enjoy the rest of your JuliaCon.
Well, thanks, Toma, for a very nice overview talk, a very interesting area. And sorry again for the technical problem. I'm glad that StreamYard, which is this software we're using, was able apparently to keep everything going, even though my system crashed. Okay, so we do have a question from Marcelo, who asked, can you extend a bit on provable safe robotics? What is the approach, and do you use neural verification.jl combined with reachability analysis?
The question was about provably safe robotics, which is the name of a course taught at CMU. Part of what they study there is verification of neural networks and using neural verification.jl, yes. They also do other things. I haven't taken the course myself. I've only looked at their lecture slides, so I don't know everything about it. Sorry.
Okay, and there's another question. Can it handle convolutional neural networks? If not, what are the challenges for doing so?
In theory, yes. So you can actually, there's a one-to-one translation between a convolutional neural network and one that is feed-forward, fully connected. Unfortunately, that one-to-one connection or that an isomorphism blows up the number of inputs to a huge number. So the limitation there is that you end up with a huge number of nodes.
So related, yeah, I mean, you mentioned the scalability issue. I mean, what kind of size of networks are you able to handle? Standard question.
Yeah, so the kind of state-of-the-art algorithms right now can handle like on the order of 10,000 node networks.
Wow.
Which is
that's pretty big, but yeah.
Pretty big in terms of 10,000 sounds like a lot, and then also when you look at neural networks with billions of nodes, you realize it's absolutely exactly.
Yeah, that's a fair point.
Yeah.
So I mean, okay. Christian says, I understand that the purpose of the package was a survey of the state of the art, but do you have plans to extend the package? Presumably he means to kind of more research questions.
We've definitely talked about it, yes. One thing we hoped to do, and I think will pursue, is to try to get all the algorithms as implemented in Julia to be competitive performance, if not better, than their original implementations, which seems feasible. Actually, many of them already are competitive, even without having taken that extra effort to do so. We have also been adding algorithms as they arise. So there's some new ones that were not in the original survey, but are coming in. Yeah, and I think there's Julia Reach has a package which depends on neural verification, which asks some more researchy sort of questions, more cutting edge questions. Also very interesting.
Okay, fantastic.
Yeah.
So I think, well, we should probably be wrapping up. The next session at JuliaCon starts in 14 minutes. So yeah, we were already planning to take the extra half hour, but now we've taken an extra 15 minutes on top of that. So probably we should leave the discussion there, or unless anybody has more to say, we can take the discussion to the set propagation channel on the JuliaCon Discord server. And after JuliaCon is over, there's always a discussion ongoing on Zulip. There's a Julia Zulip server, which is another chat piece of software. There's a Zulip stream called Reachability Analysis, which may be renamed, and we can continue discussing there with everybody. So thanks very much again to Marcelo, Forets, and Christian Schilling for organizing this fascinating symposium, mini symposium, and thanks, of course, to all of the speakers who gave such excellent talks on a wide variety of subjects, presenting set propagation in this context. Okay, thanks everybody. Have a good day.